All right, guys. So today we're going to be taking our first look at the AWR Design Environment. So for those of you who might not know or maybe aren't required to watch this video for class, AWR is a very powerful RF design tool that can be used for a lot of different things in the RF and microwave community. Now, if you were in class whenever Mark Safian gave an AWR tutorial, he mainly focused on VSS. That's going to be a system level simulation of these devices. So you can have things like a behavioral mixer or a behavioral amplifier, where you can tell it things like the noise figure, gain, conversion gain, things like that to actually describe it. But it's very sort of ideal in a sense. So AWR outside of VSS also has something called their AWR Design Environment. You might also hear some people call it microwave office, things like that. So that's actually what's going to allow you to piece together microwave circuits and actually allow you to solve some problems and see how things behave in a real, like, board level design. It's a very useful tool, especially for radar engineers who are going to have to test out their designs before they send them out to be fabricated, so they're not wasting money and things like that. So this is going to end up being pretty important, and it's good to get a nice solid footing on everything. So today what I'm going to be going through is I'm going to be going through all the topics that you're going to need to have success in the homework and have success in the class later on. So that's going to be covering just the basics of getting started with AWR. Then we're also going to talk about how you can make a schematic and add text to that schematic, and then how you can start adding actual circuit elements. So transition or transmission lines, resistors, capacitors, lumped elements, things like that. Then we're also going to be talking about how you can add graphs and measurements so you can actually see what the results are from using these different components and simulating them. And then look at some basic impedance matching networks. So looking at a practical example for how we can simulate certain designs using AWR Design Environment. Now we can actually use that to solve some real RF engineering problems. So I've actually already got AWR opened up on my screen. So you can see right now at the top, it just tells me I have untitled project. And this may not look exactly the same to yours. So depending on how you set up your AWR the first time you installed it, which I'm not going over because it involves you actually looking for the volume key for your specific machine. So I'm not going to go over the installation. But assuming that you've already gotten AWR installed, yours might look a little bit different from mine if this is your first time running it. So I'm going to go over how you can maybe change some of the basic features and maybe make it a little bit more visually appealing to you. So the first thing that you might notice is that you may not have these three tabs here on the left that say project, layout, and elements. So at the top it says project, then in the middle it says layout, and then down here it says elements. So these windows are going to be pretty important for us later on. So it's usually a good idea to have these kind of pinned right here to the side or maybe at the bottom or just somewhere where you can very easily access them. So if you don't have these at all, one thing you can do to actually make them appear is you can go to View and then Project Browser here. So Project Browser is the first name of that one that's abbreviated project. And if we click it, we can see that it just pops up here for me. Now there's a little pin here to the side. So if I click here, it says auto hide, then that's turning off the auto hide feature. So now it's going to constantly persist there. So I'll always see this project window here. Click project, layout, elements. If you don't have these layout or elements windows, you can also just click view, elements browser, or view layout manager, and it will pop these up for you. Now let's say that I've got these arranged how I want them. So usually I'm going to have project first, then elements, and then layout. That's usually the order of importance that I work with AWR in, at least. So if I have these three here, and maybe I'm working on something very important in the center of my screen, so I need to dedicate a lot of attention or a lot of screen real estate, all I have to do is I can just press this little pin button here, auto hide, and it automatically hides it for me. Then if I need to see something in my project, I can just come click over here, mess around with this menu, get an element, mess around with this menu, things like that. And then if I go back to my schematic or graph or whatever it is, it'll automatically hide. So that's one thing you can do to move these over here. But again, this isn't really a functional thing. It's more of just making everything look pretty. And then you can use the view window to make these appear and disappear as you need them. So once we've got that set, we are also going to be taking a look at some of the project defaults. So usually the first time you start AWR, it might ask you for a couple of things that you need. So maybe like default units that you want and things like that. So if you want to change that for a project, all you have to do is you can go to Options, Project Options, on my other screen. So if we take a look at global units and we click Edit Units, we can actually change the default units for a lot of things. So let's say for one design, we're working at really high frequency and we want picofarad and nanofarad, or picofarad and nanohenry capacitance and inductance values. Maybe another one, we're working with a little bit lower frequency. So now we want nanofarad capacitors and microhenry inductors. That's definitely an option that you have here. This is just a little bit to get you familiar with AWR and the menus. We'll talk a little bit more about these menus as we need them. But for now, I'm just going to make this hide. And then same thing here. You can work with a lot of settings just by going through this options window. But I don't want to dig into this too much without actually having a practical example to show you. So one of the first things that we're going to be taking a look at is how you can actually make a schematic and add text to it. Now, as you can see up here in the top left, it says that this is currently an untitled project because I haven't saved this. Maybe, for example, if you have one of the, let's see, the chirp radar system open. I'm going to go ahead and not save this. If you have the chirp radar system open, so you have just any general project open and you want to get back to a new project, all you have to do is go to File and New Project, or you can just hit Control-N. So I like hotkeys, so I'm going to hit Control-N. I need to click on the window first. So if I hit Control-N, it will clear everything out. It'll usually ask if you want to save, if you have any pending modifications. And now, this is still just untitled project, so we're back to where we were before. Usually the first thing you're going to want to do is save your project. So if you save project as, it'll open up a nice window for you. So right now it has it in my root directory. And if I just go to maybe, if I go to my documents, I can just do AC AWR tutorial. .emp is going to be the project file, and that's where it keeps really everything in your project. It keeps it all in that EMP file. That's just the only file you need, and now you can see up here on the top, it's changed the name to AC_AWR tutorial.emp. So now this is actually a project that I have made, and I can save. It's now in my file system, and it's not just untitled project anymore. So I don't really have to worry about losing much progress. So now that we've got our project made, and hopefully we've saved it at this point, the first thing that you're going to do, and this is going to be for your homework too, is that you're going to need to know how you can add text to a schematic. So before we can add text to a schematic, we first need to create a schematic. And this is where we can talk a little bit about the project browser window. So if we either go to View Project Browser, or we just hover over this project area here, you'll see that this project up here in the very top, that's going to be our project file that we just made. So that's holding everything that we have in AWR. Our schematics, our graphs, everything are going to be underneath that project folder or that project file. Now, we can see that there's not much to expand. We have some wizards down here, which Mark Safian talked a little bit about, but there's really not too much to expand. We have our global definitions already expanded. It's kind enough to give us a global definitions file already if we need to make any global variables, but there's not much to expand right now. We have to add a little bit to this project ourselves if we want to have anything cool here. So one thing we can do is if we go to circuit schematics, if we right click on circuit schematics, we can click new schematic. We could also import or maybe even link to another schematic if we have one that we want to look at. But for us, we want to just make a new schematic. Now it's going to pop up a window. It's going to ask us to enter a name for the new schematic. And I'm just going to call this one group names. Okay. So this is our schematic here. Now we have a different window popped up. We have a grid and everything like that. We can see that on our project browser, now underneath circuit schematics, we have a schematic called group names. So this is where all of your schematics are going to be listed at underneath this circuit schematics tab here. Now I'm going to go ahead and just delete this so I can show you a couple of the other ways to make schematics. So there's one way that we saw, go to project, right click on schematics and click new schematic. But there are multiple ways that you can actually create a schematic in AWR. So one of the ways you can do it is you can press project, go down to add schematic and new schematic. Or you can also just use this little top window here. So this little top toolbar right here, right now it has some stuff like save. And so if we go ahead and save, which is a good idea, we can move over and we can see that there's one that says add a new system diagram, which is going to be more on the VSS side of things. We can add an EM structure, which if you're in Dr. Syed's antenna class, you're going to be familiar with by the end of the semester. And we also have add new schematic, and this is what we're hunting for here. This is going to be the best way to add a new schematic. It's very, very quick. It's least number of clicks. So if we just click add new schematic, and I'll make my schematic called group names. Okay. So now we can just maximize this window. If I bring the status window down a little bit, we can maximize this window and have it take on a full screen. Now we have ourselves a blank schematic here. So if I scroll, you can see on the right-hand side, the scroll bar is going up and down. If I control and then scroll, we can actually zoom out and zoom in. And then shifts and scroll will actually let you scroll left and right. Now, if we just press, for the first thing, what we want to do is we just want to add a little bit of text to our schematic. So the first thing for the homework that this is really built for is going to be adding the names of all your project groups into these schematics. So the names and R numbers of these project groups. So in order to do that, we can actually just look right up here at this toolbar. So if we look right up here at this toolbar, what we'll notice is that it actually changed quite a bit since the last time we looked at it. If we close this schematic, we can see that we have a pretty short toolbar. But if we open our schematic one more time by clicking the project browser and double-clicking on our schematic group names, then we can see that once we have the schematic window open, this toolbar expands by quite a bit. So we have a lot of new stuff here. So what I'm concerned with right now is this capital T. And capital T is text. Usually if you've worked with a computer before, you could have guessed that. But if we click on this text tool, it will allow us to actually place a text box in our schematic. So if we just place it right here in the center, it doesn't look like anything happened right now, but if we start typing, we can see that it actually allows us to put text in our schematic. So if we put group members, colon, now if we press enter, what happens is that it closes the text tool. So that says that we're done entering text. The one thing we could do is we could maybe add another text box down here, but that's a little bit clunky, and then we have multiple text boxes. That can be tough to deal with. So if I press escape to close out that text tool, what I can do is if I double click on this text here, press end and go to the end. If I, let's see if I guess it right, shift enter. So if I click shift enter, then that will actually do a new line. So it does a new line in the same text box, and it actually allows us to continue typing. So if I say the first member of our group is Thor Odinson. Okay, so Thor Odinson, comma, let's just say his R number is 1, 2, 3, 4, 5, 6, 3, 2, 1. Okay. Now that could be the first member of our group, and then we have, let's say, another that's Tony Stark, and we can make him R987, 4, 5, 6, 3, 2, 1. Just some, whatever your R numbers are, don't follow me exactly. So whatever your group's R numbers are, you can include their names and R numbers here. And this will actually, once we press enter one last time, it will actually stick into our schematic. So now we can move around our schematic and not have to worry about messing up our text box. That is set in our schematic. Now, one thing that you might see happen frequently is that you might, maybe if this is a very large schematic, you might kind of get really zoomed in here on this TONY, and then you're not going to be able to see anything else. Now, if it's a very large schematic, it can be tough to sort of zoom out and have to zoom in different places. So if you just maybe need to take a screenshot of your computer or something like that, something that you need to put in a report, there's a really easy tool. It's just one key that allows you to see everything in your schematic. So it goes from wherever you are to showing everything in your schematic very easily. And that's just the home key. So if I press the home key, it will zoom out or in and move the window around so that everything in that schematic window is shown at that current time. So let's say if I move our status window all the way up here, and let's see if I press home again, it'll make sure that everything is visible here. In the same way, if I bring it down even further, it's going to ensure that everything stays visible all the time. So if I've got a really large complex schematic and I need to take a wide angle screenshot, I can just press home and it'll bring us there. So that's a good key to kind of remember in the back of your mind, is that home kind of resets the view. So now we've got a schematic and we've added some text. You can play around with this a little bit more if you want to see how different things work. You could also maybe right click and go to properties and see maybe how you can change the font to something else, and then maybe even change the height too. So make the height a little bit larger, bold, or italic. But that's going to be sort of on your own time. So that's not going to add really any technical benefit to this tutorial. So I'm going to leave that to you. Now, it's important to Control S and save every once in a while so you don't lose any of your work. Thankfully, it's not like Cadence, so you're not going to get shut down from the server or anything like that. But it's still a good idea to save your work every once in a while. Now, we've got our schematic done. We've got our group member names placed. Now, let's actually look at how we can make a little bit more technical schematic. Okay, so let's make a little bit more technical schematic and see maybe how we can use AWR to accomplish some cooler things besides just placing text. So I'm going to make a new schematic. So thankfully from this schematic window, they still have the new schematic tool at the very top there. Now I'm going to call this one transmission line, because we're going to mess a little bit with some transmission lines and some lumped components, okay? Now, we have our blank schematic again, and we've learned how to add text. But if you don't want to add text, if you want to add something of engineering substance, that's where the Elements browser is going to come in handy. So if we go to the Elements browser, what we'll see is that we have a ton of different circuit elements listed here. You'll also notice that a lot of these are expandable. So we can expand, 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 and get a lot of different things. Now, the first thing that we're going to be interested in is an ideal transmission line. So an ideal transmission line is going to be lossless. It's going to provide a perfect phase delay at a given frequency, and it's going to pretty much act like the ideal transmission lines that you would learn about in class. So they're going to work very, very easily and good for some conceptual stuff when you don't want to worry about parasitics. Now, if we're going to use an ideal transmission line, you might guess it's underneath the transmission lines window. So if we click transmission lines, we'll see that nothing happens down here. So this is where it's going to list all the stuff that we can use in our schematics. So we don't have anything listed here. Let's expand. Hey, we could look at coaxial if you're interested in a coaxial line, but we're not for this case. We're interested in phase. So phase transmission lines make sure that the transmission line, whatever signal is going in, is phase delayed a certain amount going out. So it acts like a perfect transmission line and provides a phase delay. So we can look at a bunch of different transmission lines. So they have coupled lines, grounded shield, transmission line 4, all this other stuff, an open circuit transmission line. But what we're going to be mainly working with is this T-Lin model. So we're concerned with this T-Lin model. Now, if we just double click this, for example, and go to our schematic, nothing happens. So what we have to do is we have to go to our elements window, click, hold, and drag it into our schematic window. Now, we can actually see that it's got that little sort of gray outline of this transmission line kind of hovering around. And if we just pick a place for it and then left click, it'll actually drop that transmission line right in the center. Now, there's a couple of properties for this transmission line that we might be concerned with. So Z0 is Z0, the characteristic impedance of that transmission line. And we're going to keep that at 50 ohms for right now. So we're going to assume that this is a 50 ohm transmission line. Now, EL is the electrical length. So it's not the actual physical length, it's the electrical length in this case. So this is, going to be the pretty much the phase delay in degrees that it applies to any signal. Now, F0 is going to be the center frequency, and this one can actually be pretty important. So if you remember, different frequencies, they're going to have a different phase delay for a given transmission line length. So that's why we're concerned with the electrical length. This electrical length is 90 degrees, but that's only valid at that center frequency, because if we have a higher frequency, let's say it's 50% higher, then that phase delay is going to be 50% more, okay? Because it's going to go through 50% more cycles by the time it actually gets to the end of that transmission line. So electrical length and F0, the center frequency, are going to be pretty important for us. So let's say that our F0 is going to be, let's just do 2.4 gigahertz. And again, if your units aren't in gigahertz or something like that and you want to change them, all you have to do is go to Options, Project Options, and click on Global Units, Edit Units, and you can do it there. And let's keep our electrical length at 90 for right now. Now, we also are going to keep our Z0 at 50 ohms. You're welcome to change this if you want to. Now, on this other end, we just have it connected to nothing pretty much. So it's just an open circuit. So let's, just as an example, let's add another element to this schematic. So the element that I want to add is just a regular old resistor. Now, a resistor, you could model it a lot of different ways, and some are going to be more accurate than others. But for just a quick solution, you usually want to use what's called a lumped resistor. So it's going to assume that it's just a perfect V equals I times R resistor. None of this RF mumbo jumbo microwave stuff is going to start happening here. So we're going to assume it's a perfect lumped element. And if you're looking for a lumped element, you guessed it, look under the lumped elements window. If we expand lumped elements, we'll see that there is a resistor one here. And we're going to use this RES value, res. So click and drag this into our schematic. And we can do a couple of things. We could just connect it end to end perfectly like this. Or if I click this, press Control X will cut, and then Control V will allow me to paste it. I can set it over here and then connect it this way using this little wire tool. Or there's an even better way. If we cut it and paste it again, you might see this little dashed line that it has between the transmission line output and the resistor input. Now, if I hold Shift and left click while that dashed line is on the screen, it will actually go ahead and connect it for me. So if you need to make a quick connection and you don't want to manually go through and make this connection, you can use that little tool, that little hotkey to make those connections a little bit faster. Now, same thing, this resistor doesn't have anything on the end here, so we're going to need to connect it to ground. We're going to assume that this is, let's just say it's a 75 ohm resistor, and we're going to connect it to ground. So for us to connect to ground, there's a couple of options. You can either come up to the top and pick this ground element here, or you can do my favorite and just hit Control G. So Control G will again bring up this little ground symbol, and if we shift and click while that dash line is here, it'll automatically connect it. So now we have a pretty basic schematic up and running. Let's see what happens if we click the Run button. So for VSS, we use this Run/Stop System Simulators, but for the AWR Design Environment, we're going to use Analyze. So Analyze will actually start analyzing all these schematics and try and generate the results that we're asking for. Now what you can see is that whenever I click this, nothing really happens, right? We don't even get anything down here in the status window. And that's because this schematic isn't quite complete, right? So AWR doesn't want to do work that it doesn't have to. And that means that it's not going to analyze everything about this circuit until it knows what we want out of it. So it doesn't know what we want out of it just quite yet. So we need to tell a few more things. Now, what we're going to tell it is we're going to actually tell it what we want it to measure. That way it's only going to simulate what it needs to provide us that measurement. And the way that we can do that is by making a graph. So a graph is sort of an analog to the schematic. So a schematic, the results from a schematic are going to come up on a graph. So if we take a look at our project window, we'll see down here graphs. You can right click and hit new graph, or you can come up here to the top and hit add new graph here. I'm going to elect to do that. Now we're going to start with a rectangular graph. And I'm going to name this one input impedance because that's what I want to measure for this. If I hit enter, it'll create us a graph here, and it actually makes us a new window up here at the top, so we can very quickly switch between some different windows here. I'm going to go ahead and close group names because we're done with it. Now we can look at this input impedance graph. Now let's take a look at the project browser one more time, and I'm going to pin it here for now. So if we take a look at this input impedance graph, it's sort of like having a schematic with nothing in it, right? We've made a new graph, kind of like we make a new schematic, but we haven't added anything to it yet. So this graph is just here, it knows the title, and it's given it a very basic X and Y axis, but it doesn't know anything yet of what we want to measure. It's not smart enough to say that we want the input impedance yet. So what we need to do is if we click on our graph in the project browser here, we can right click and hit add new measurement, or we can right click on the graph, hit add new measurement, or if we come up here to the very top, we can click this tool here, add new measurement. They all get you to the same place. Now, what we're concerned with is the input impedance, and where we will find that is if we come up to the top here on measurement type. Input impedance is a linear measurement, so we're going to click on linear. And if we scroll all the way down, we'll see Zn. Now, Zn is going to tell us the input impedance at a port, and that'll be important later on. And let's say we just want to look at the magnitude. Now, if we just click all sources, we can see that that schematic that we made, we have all sources here, which is telling us, telling AWR we want to measure everything that it can. But we'll see that our schematic isn't even popping up under this data source name window here. And that's because we don't have a port defined yet. So I'm going to go ahead and hit cancel here. And if we run back to our transmission line schematic, we'll see that this is again just an open circuit. So AWR doesn't know if we want to actually connect something to this open circuit and measure it, or if we want it to model the open circuit there. So if we want to actually perform a measurement at a location, we need an RF port. And the way that we do that is pretty easy. We can just come up here to the top and click port on our schematic, or you can press Control P. And it'll bring up this little window. And if I bring it here, hold shift and then left click, it'll connect a 50 ohm port into the input of this transmission line. Now, if we go back to our graph, we can right click and add new measurement again. And we go to linear, scroll down to Zn for input impedance. And now if we go to data source name, transmission line is actually appearing. So the port index that we want is going to be port 1 because on our schematic, the port we just added was port 1. And for the sweep frequency, we're going to assume we want our frequency on the x-axis. And we're going to have to play with this a little bit more, but for now, leave it as used for x-axis. We're still looking at just the magnitude, so not necessarily the real or the imaginary part. And let's just hit OK. Now, right now it's grayed out, and that's because it just now learned that we want it to simulate input impedance. So we need to analyze one more time before it will actually display anything. So let's hit Analyze. Okay, so now we can see on this graph, we have what looks like a really nice line between 1 and 2 gigahertz. So we have what looks like a very, very nice line between 1 and 2 gigahertz. But what we're going to find is that, well, in real life, it's not going to look this good. It's not going to look like this perfectly straight line. We're going to expect maybe some curvature to be appearing here. Now, the reason that we just have this straight line here, if we close this window, now we can come up to our measurement and right-click on it, hit Modify Measurement. And if we take a look at this sweep frequency, it's looking at the frequency in the document, which only has 2 frequencies defined. So it's only going to simulate at 1 gigahertz and 2 gigahertz, and then do some linear interpolation between the two. So that's why it looks like we have this perfectly straight line. We just have the 2 endpoints defined, and it's drawing that straight line between the two of us to try and fill in the gaps. So if we don't want it to do that, we can hit Cancel here. And this is going to be something pretty important. We can click Options, Project Options, and then click on the Frequencies tab. Now we can see that it's only looking at 1 and 2 gigahertz in this case. So we want to actually replace these with a little bit different range. So let's say instead we want to sweep all the way from 1.4 gigahertz all the way to 3.4 gigahertz, and that 2.4 is going to be right in the middle. So let's say we want to start our sweep at 1.4 gigahertz here. We're going to stop at 3.4 gigahertz. And for now, let's say we just want a 0.1 gigahertz step. So what we can do is we can actually press Apply, and it will, as long as we have Replace here, if we just have Add and we apply, it'll just continue adding it to the end, which may not be good. But if we hit Replace, it'll actually replace that entire sweep with what we just defined. So now we have it sweeping from 1.4 to 3.4 in 0.1 gigahertz steps. Now you want to make sure you don't make this too small, because if you make it too small, then it's going to have to simulate 2,000 points. And if it's a bigger schematic or a bigger design, that can take a really long time. But maybe a nice happy medium will be 0.01 gigahertz. So 10 megahertz steps, it'll only be 201 points, and we can press OK here. So now this is grayed out again because it hasn't updated the result, and we need to analyze one more time. So if we analyze, now we can see a little bit more curvature, maybe a little bit more of what we were expecting. So what we're actually seeing in this case is we're seeing the input impedance at this 50 ohm port after having this 75 ohm load impedance go through 90 degrees of transmission line at the 50 ohm transmission line. So because the load and the transmission line aren't matched, we're getting this little mismatch here at our port, which is why we're seeing the magnitude of the impedance be not what we quite expect. But if we need a little bit more information, we need to actually see the real and the imaginary parts. So if we right click on here, click Modify Measurement again, I'll close this window. We can change it to be from magnitude to just the real part of this input impedance, so just the resistance. If we press OK and run it one more time, we're seeing that the real portion does still look pretty similar, but it's slightly different. So the real portion is going from 42 ohms parabolic back up to 42 ohms. And then if we want to see the imaginary, we could make an entirely new measurement, or you could just duplicate this measurement here. So if we right-click, Duplicate Measurement, it's going to duplicate this measurement. It's bringing up the window for us again to see if we want to change anything. And if we just change it to the imaginary part, now it hasn't simulated it yet. So if we rerun it, now we can actually see the reactance. So if we look at this reactance, we can see that as we move further up in frequency, so at 3.4 gigahertz, the input impedance now has sort of inductive qualities. So it has a positive reactance, meaning it's inductive. And if we move at lower frequencies, it's more capacitive. Okay. Now, let's take a look at just a 50 ohm load. So if we have a 50 ohm load, 50 ohm transmission line, we're expecting pretty much 50 ohms constantly. And that's what we get. So this is sort of just verifying our sanity. We can click on this window here if it's kind of in the way. You can move it out of the way, and you can use these little squares here to maybe make it smaller and shrink it. That way it doesn't block any of your graphs. Now this looks a little bit more like what we expect. So we have 50 ohms here, and this can allow us to do some pretty cool things. So one of the homework examples that we're going to be taking a look at is going to be implementing maybe a sort of a trivial transmission line problem in AWR just to verify the results. So if we take this transmission line problem, I'm going to go ahead and delete this load. Let's just take a look at this open circuited transmission line here. So if we have just an open circuited transmission line, it's 90 degrees for its electrical length. If you've been paying attention in class, you should probably know that this 90-degree, this quarter wave transformer is going to turn that open circuit into a short circuit at RF. So if we take a look at our input impedance and run this one more time, we'll see that at these, at this large sweep of frequencies, we have a 0 ohm resistance, which is more or less what we expect. And then at 2.4 gigahertz at our center frequency, this pink line, the reactance line, goes to 0. Okay, so that reactance line goes to 0, so it's like we have 0 ohms resistance, 0 ohms reactance. That's a short circuit. So even though we don't have a short circuit truly, for AWR and for microwave stuff, it's actually going to be looking like a short circuit. So it's an RF short. Similarly, if we just have this shorted to ground, so if we press Control G to add a ground terminal here and rerun it, then at that center frequency, it pops all the way up to this huge number, which is effectively an open circuit. So that quarter wave transformer can transform a short circuit into an open circuit. Now, we can actually get a little bit more creative, maybe add a few more things here if I delete some of these connections. So if we add, let's say, another quarter wave transformer, if I'm right-clicking to rotate, if we add it maybe here, and then let's go ahead and add ourselves a resistor one more time. So let's add a resistor at this point. And we're going to make this resistor 50 ohms to ground, right? So if we don't have that ground connection, this is just a lumped resistor, so the current in is going to be 0, and it's not even there. So if we don't have this ground terminal, then it's not going to be correct. And I'm going to scoot it over just a little bit to maybe make it a little bit more symmetric. Now, all of these are 90 degrees. We can tweak this a little bit if we want to, but this can maybe give us a little bit more of an interesting problem to experiment with. So just off the theoretical side of things, we know that this open is going to be transformed into a short. A short parallel with anything is going to still be a short. Now, this short is going to be transformed, this short is going to be transformed thanks to this quarter wave transformer here into another open. So maybe we're expecting an open circuit here at this first port. So let's check it out. So right now it's grayed out. We don't know these results are correct yet. We can run it, and we still see that same open circuit at our 2.4 gigahertz center frequency. Now let's change this up just a little bit more. So let's change this up, and let's say that this is now 180 degrees. And then we have, get rid of this, let's say we have a 50 ohm resistor in series. So now let's try and think about this one more time. So we have an open turning into a short here. Short parallel with 50 is still a short, and this short turns into an open here. So even though we have this 50 ohm series here, we're expecting it to still be an open, because 50 plus an open is still going to be an open. Oh, did I think about that right? Oh, I forgot that I changed this into 180 degrees. So 180 degrees is going to keep this still a short. So now, even though it's not 50 ohms all the way around, if we look at our center frequency, it's at 50 ohms and the reactance is 0. So this allows you to sort of play with these ideal transmission lines to get a sense for how you can actually use them and how you can implement them to maybe do some proof of concept simulations and things like that. Let's go ahead and close this. Now that we've got some of this more advanced stuff done, we can close some of these. And now what we want to actually look at is we want to look at a practical example of designing an impedance matching network. So we're going to design an impedance matching network using an L network. So we're going to use lumped components. So we're going to need a new schematic. So I'm going to make a new schematic here. I'm going to call it L network. Go ahead and maximize this, and I'm going to run through it just a little bit quicker now, since we've gotten some of the basics down pretty easily. So if we run through this a little bit quicker, we know the first thing that we need is we need an impedance to match. Now, there's a couple of ways that you can implement this in AWR. You could use combinations of maybe resistors and other lumped components like capacitors and things like that. Or they also have inductors here, if you look for IND inductor. And you can change their impedances and things like that to actually implement these load impedances. But there's something that I like just a little bit better, and I think makes things a little bit cleaner. So if you take a look at resistor, underneath resistor, there's something called a load. Now that load, it says here, is just a ground of resistor. And if we bring this into our schematic, it's just a one-port device, so it only has, the input port, and the other side is connected to ground, so we don't have to manually connect to ground ourselves, which is kind of nice. Now, something else that's nice is that even though it says 50 ohms here, and you may be inclined to say I can do 100, I can do 25, I can do whatever real resistance I want. You aren't confined to only real resistances. So you can actually implement impedances in a load. So you have a resistance and reactance in this load. And the way that you do that, let's say we're going to match 100 and then minus J times 50. Okay, so let's say we have 100 ohm resistance and then minus J50 reactance. And this can actually be our complex load. So if we have a complex load that's defined in this way, we can implement it in AWR using this element here, the load element. Now, it's important to make sure that you have that star there, because if you just have J50, it won't kick anything back now, but it'll actually think that J50 is a variable, and it'll say later on, J50 hasn't been defined, so make sure you include that J times 50, because it knows what J is, it knows what 50 is, but it gets confused with J50. Now, let's start off simple, and let's just get a sense for our problem. So let's get a sense for our problem. We're going to measure this load impedance, and if we're going to do some impedance matching, we're going to want a Smith chart. So before we can add a Smith chart, let's add a port, add something for us to measure, and I'm going to make it a little bit further away because we know we're going to be adding things later on. And now we can go back to our project browser, or just click up here, and I'm going to say L network Smith chart. Now, don't hit create yet. We don't want a rectangular chart because that's going to be an X and a Y axis. We actually want it to be a Smith chart, because it has a Smith chart built in, and it'll automatically convert a lot of these measurements into a Smith chart. So we hit create here. We can see that now we've got our Smith chart generated, and right now we have our impedance grid. So if we do the same thing, we can either hit right click, add new measurement, or up here, click add new measurement. We can add in, we'll stick with ZN in this case. So we'll add in this input impedance to our Smith chart. Now for our data source name, we don't want it to be transmission line, we want it to be the L network. And we're measuring at port 1, and we're going to sweep this big frequency for our x-axis, so that wide frequency range. Now, we're going to keep it complex because we don't want it to do the conjugate or anything like that. We only want it to be complex. And we don't have the option to do real, imaginary, magnitude, anything like that, because the Smith chart actually is in the complex domain. So we can't just do the magnitude because that'll remove information from the Smith chart. So now if we just press OK, it's grayed out. We don't see anything yet. And if we run this, what we'll see is that we will actually see this point on our Smith chart here. So now we have this point on our Smith chart. It says R is 2 and X is -1. So again, these are normalized coordinates here. So R2, if we denormalize that, is 100. -1 is -50. So that's the real and real resistance and our reactance here. And that matches with what we see in our L network. And now we need to actually design the circuitry that we're going to use in order to match this. Now, there's a couple of ways you could do this. You could use the closed form equations and things like that, derive the equations, maybe do some reading in a book to figure out the exact values that you need for maybe your inductor and capacitor to match this. Or you could use some of the tools that AWR has and maybe make your life a little bit easier. So let's get started with just a very general matching network. So we're going to start with just an inductor and a capacitor. But before we can get started actually doing the matching and figuring out what components we need to add and where, we might notice that this Smith chart is missing something. So right now we just have the impedance grid, which gives us a lot of information, but it doesn't give us everything that we need. So if we're doing impedance matching, it can be a lot easier if we have an impedance and an admittance grid all at once. And there's a good way of adding that into AWR. So if we right-click on the graph here and go to Options, move this window over here so you can see it. If we go to Grid, make sure you're on the Grid window, you'll see that it has an impedance grid and an admittance grid. An admittance grid is probably not checked. So if we check admittance grid and then hit Apply, now both the impedance and the admittance grid is shown on our Smith chart. This makes it a lot easier for us to actually perform this matching using the AWR tools at our disposal. Now, what we can see is that, if you've been paying attention in class again, there's two ways that we can go about getting this matched using just two elements in an L network. So one of the ways is we could travel along this constant, or let's see, yes, we could travel along this line in the admittance grid up until we hit this constant resistance line and then go down. Or we could travel down this same line and then go up along this constant resistance line here. So there's two main ways that we can get to that center point. So this first one will require us to add an inductor. Since we're moving up in the Smith chart, that's going to be adding an inductor in this case, and back down with a capacitor. So it could be inductor and then capacitor. And then if we check this one, it'll be adding a capacitor and then an inductor, since we're going down and then up. Now, something that's important to note is that since we're moving along this line in the admittance grid, that's going to be the constant conductance circle, right? So this is the constant conductance circle. And that means that the conductance is going to stay constant, and we are going to be modifying the complex part of the admittance here. So that means we're going to be adding things in parallel. So that means we're going to start off with a parallel lumped component, and then we're going to end with that series lumped component. So if you're familiar with L network matching, you know that you're going to need one series, one parallel typically, but there's all sorts of different ones. But we're going to start off with a parallel component. And I am going to go ahead and decide that I want to move along this top. I want to move to the top first and then move down here. And that's going to be using an inductor in parallel to move us along that constant admittance line, and then a capacitor in series to move us along that constant resistance line. Okay, so I'm going to use an inductor in parallel. I can get that from elements, then move to inductor, and then I and D. So an inductor in parallel, and I'm just going to add this here. Now, again, the inductor is a lumped component, so if the other side isn't connected, there's no current that's going to be able to flow, and it's not going to have any impact. So if we press Control G at a ground terminal, then this inductor is now connected to ground. Now, similarly, I'm going to delete this line, and then we can add a capacitor in series here. I'll click Shift, that'll connect one line there. I manually connect this other. Now, right now, these values are starting off at 1 picofarad and 1 nanohenry, which is okay. So if we want this capacitor to have pretty much no effect at high frequency, which is kind of what we want right now, just to see the effect of the inductor only, then we need to make this a very high capacitance. So capacitance is a short circuit, 1 over j omega c, and then as that C gets larger and larger, the the impedance of the capacitor gets lower and lower, and that means that it's going to have less of an effect on the circuit in the series connection. So if we make this, let's just say 1,000, so 1 nanofarad, this should be large enough at 2.4 gigahertz for us to hopefully not see any impact. Now, if we move back to our L network on the Smith chart and we run it again, what we'll see is that now that dot has turned into a line. Now, what's tricky is that that line was always there to begin with. It's just it was collapsed in on itself, and it looked like just a point. Because this load is only defined pretty much by 100 minus J50, it's going to be that same impedance at all frequencies. So it doesn't take into account things like admittance and how it changes with frequency. So now that we've added these lumped components, that dot has turned into a line. But it's real easy to make it back into just a dot at the center frequency. So if we right-click and modify this measurement, instead of having our sweep frequency using it for the x-axis, we can actually scroll down and just pick our frequency of interest, like 2.4 gigahertz. Press OK. And now we just have a single dot here. So now we just have that one single dot, and that's going to allow us to, do a little bit more tweaking here. So what we can see is that, let's go ahead and make this a little bit larger, see if there's any impact here just to verify. So we can see that it's starting off here, and as we increase it, didn't really move much. So now our capacitor pretty much has very little effect. We're only looking at the impacts of the inductor. So if we take a look at this inductor, if we change its value to maybe 10 nanohenries, what we'll see is that now this has changed position. So now it might be a little bit closer to what we wanted. So maybe if we change it to 8 nanohenries, we might get just a little bit closer. But going back and forth like this can be pretty tough, right? And AWR has realized that, and they implemented a tool that makes our job a lot easier called the tuning tool. So on your schematic view, if you look up here in the top toolbar, you will see that there is something called a tune tool. So if we click this tune tool, and we click the value that we want to tune, so we can see here it actually looks like a screwdriver symbol and it has that little rotating arrow. We can click on this 8 nanohenry value, and now it's in blue. I press escape to close the tool. If it's in blue, that means that we are actively tuning it, and that means that we can very easily change that value and see how it impacts the result. Now if we go back to our Smith chart, we haven't changed the value yet, so it's still blue, but we might as well rerun it. Now we can come up here and we can click Tune. So there's a tool here that says Tune. It's not the Tune tool, it just says Tune. And this will open up another window. And what we'll see is that it tells us the document that it comes from, the element, the parameter, and then the step size, lower bound, and upper bound. So if we actually modify, or if we move this little slider here, we'll see that it'll actually change the position of our impedance, and it changes it in real time. So if we start off with a really high value, let's say 100 nanohenries, this is closer to where we started off in the very beginning. If we reduce this, we'll see that at a certain point, we get really close to that value that we want. So maybe to have a little bit more fine-tuning adjustment, I can move this back down to maybe 10. If I'll make our lower bound 5, maybe. I know it needs to be somewhere in between there. And I'm going to keep our step size at 0.1. So if we move around here, we can get to a point, looks like 5 is still too large. Let's make it 4. And I'll go ahead and change this to be 6. Give us a little bit smaller window. If I move to about 4.8 and I click on this part here, we can see that the real part of the impedance is now pretty stinking close to 1. And if I move it down to 4.7, it actually looks like it's a little bit further away. So for real engineering, you can always get a theoretical solution that gets you right in the exact answer. But for real engineering, if you're looking at Mauser, they're not going to sell a 4.86932 nanohenry inductor. They might sell a 4.8 nanohenry inductor. So this allows you to sort of set some constraints whenever you're tuning and see how this might work with real components versus just using these sort of made up ideal values. Now, once I'm done with this, if I want to lock in this value and make sure I don't accidentally move the slider anymore, what I can do is I can just hit this tune button here. So uncheck it. It'll automatically take it away. If I look back at our schematic, now it's back into black, so we're not tuning it anymore. Now for this C1, I can do the same thing, hit the tune tool, tune C. And now, since we're at 10,000, it's going to have a pretty large value. Let's say we want to make our lower value 0, and go ahead and set our value back to something more realistic like 10, and make our upper value 10. So now what we can see is as we are moving our step size, keep it at 0.1, as we are moving this value, we're inching a little bit closer to that center point along this constant resistance line. And if we tweak it just enough, you can see that we get to a point. I'm going to make sure that we're not moving too much so I can get a little bit more fine tuning. Make sure our step size is right. You can go through this pretty easily and change the step size and the value if you need to do it in more real time or make more discrete values. So what we can see is that we have maybe 3 options. We have 1.2 picofarads, 1.1, and 1.0. And of those 3, 1.1 looks like it's going to get us kind of the closest to that center point. So 1.1 looks like it's going to be good for us. I don't want to tune it anymore, so I'm just going to unclick this tune button here. And now we can see that at our center frequency, we are pretty much matched. We are at 0.997, 0.998, and then our reactance is 0.01. So we are really, really close to a perfect match. So for all practical purposes, this is pretty much matched. Now, if we want to see this result in maybe a different way versus just on a Smith chart, what we can do is we can actually make a rectangular graph to see maybe the input reflection for this matching network, to see maybe how broadband of a match it is. So the way that we can do that, if we go back to our project, we could add a new graph. Let's make this one L network S11. We don't want it to be on a Smith chart. We want it to be on a rectangular graph. We're going to create it. Now, if we add a new measurement, make sure our data source is L network. If we expand this linear tab on the measurement type screen, what we'll see is we can go to port parameters, click S for our S parameters, and then it will actually go ahead and automatically populate some of these. And since we don't have any other ports, the only thing it's going to let us measure is S11. Now, in this case, we do want to keep our sweep frequency. We want to use our frequency as the x-axis. So we're going to use our frequency for the x-axis, and let's say that we're only concerned with the magnitude of S11 in this case. We could look at it in linear terms, but I think it's more productive to look at it in dB terms. So if we just press OK, it hasn't simulated for it yet. So if we click Analyze one more time, now we can actually see the results of this input match network that we designed. So as we expected, at 2.4 gigahertz, we have sort of the lowest, excuse me, the lowest return loss here, or excuse me, we have the lowest S11 because it's almost perfectly matched at 2.4 gigahertz. And then as we get further away from that center frequency, the match gets worse and worse because we haven't designed for there. If we're going to look for the bandwidth, maybe we want to look and see where it reaches minus 10 dB. We can actually add markers to this graph. So if we want to add some markers, press Control M, and then click on this point anywhere, and it'll actually add a marker for you. You can drag this marker around, and it'll stay stationary at this point. So one thing you can do is you can move this around manually and try and get it really close to minus 10 dB. You can see that's kind of a pain, right? So that's kind of a pain, and you're not going to be able to get exactly right on some of these. So one thing you might want to do is you can right-click on this marker. You can click Marker Search. And if we click Find an X value, or excuse me, find a Y value, and we look for minus 10 dB. And it's going to ask us to search right or search left. In this case, we want it to search right because we know that the minimum is, or the minus 10 points to the right. If we click search, it'll automatically move it to that point. So now we know the minus 10 point is 1.906 gigahertz. Same thing if we keep this window open, click Control M, add a marker here. As long as we have this marker selected, we can click Marker Search, minus 10, keep everything the same. We're still searching to the right. Hit Search. Maybe we do need to click it again. Marker Search, minus 10, search right. Oh gosh, that's why, because there's no minus 10 point in this graph. Okay, so yeah. If you guys notice that, then you're definitely doing a lot smarter than I am in this case. I would have pulled my hair out for a while. So maybe if we look for minus 15 and now we're searching through the left, we can search and find, oh goodness. Maybe we're not going to be able to do that. I'm not sure. Okay, well, this is good and confusing for me. There we go. Okay, so now we're getting it to work. Okay, so maybe that's how we can find maybe the minus 15 point. Now, same thing, if we can close this, if we would just want to find the minimum, you can have the marker point only to the minimum, things like that. So you can use these markers to help highlight some of the exact values in your graphs. Now, the last thing that I want to talk about for this one, now that we've seen the S11 and everything like that, is I want to talk about how you can actually use practical components in AWR. So up until now, we've used a lump network where we have the L network lump components. And as long as you're buying good lumped components, maybe making sure the self-resonant frequency for inductors is a lot higher than where you're working at, then this can give you a pretty good approximation. But what you'll find is that for this transmission line model, these transmission lines don't behave anything like real transmission lines. They don't take into account loss, they don't take into account a lot of parasitics, and they don't take into account things like junctions and how those might impact your circuits. So for us to actually use real transmission lines, we're going to need a new schematic to show how we can actually implement some transmission lines. So let's say that we're going to make a new schematic, and we're going to call this microstrip match. Okay, so we're going to call this microstrip match. I'm going to close all these other ones. So let's say I've got a bunch of windows open. If I hit Window and then Close All, sometimes that can be quicker than just reopening the one that you want. So sometimes that can be quicker than having to manually go through and change everything. That's not even the one I wanted. So now we have this microstrip match. Now let's go ahead and start off with an ideal load, and I'm going to go ahead and steal it from our L network graph. So let's start off with this ideal load. And let's say that instead we're going to make it 100 minus J 100. Okay, so make it a little bit different, a little bit tougher on us. Now, what we can do is we can start off the same way, probing this port. But what I want to show you is how you can actually use real transmission lines in this case. So to start off, let's just add a real transmission line coming from the output or from the input of this load. So I'm going to show you how you can use microstrip line, but you can use the same thing with strip line, coplanar. You can use use a lot of different types of transmission line, but I'm going to start off with microstrip. So if we open this microstrip window, the first thing we're concerned with is lines. So we're going to be concerned with the microstrip lines. And if we take a look, we can see there's a lot of different options here. But the one that sounds most appealing to us is going to be this M line. If we click and drag this, it is the closed form of the microstrip line. Now you can see a couple of things here. You can see that number one, it's purple, and we'll talk about why that is here in a little bit. And you can see that it no longer has electrical length and center frequency. It now just has the width and the length of that transmission line. So like I said, this is an actual real transmission line. So it's not going to care about the electrical length. It's going to tell about the physical properties that you give it. Now, if you're just starting off, you might say, well, I don't know exactly what the width and length need to be for certain cases. AWR has you covered. So if you click Tools and this TX line tool, I'll bring it over here. It opens up this TX line tool that they've had for a really long time, but that's really, really handy. So if we say we can pick a dielectric here that's maybe a little bit more realistic, so it has RT Duroid 5880, and it'll automatically populate some things like dielectric constant and loss tangent. That's just going to be properties of the dielectric. And you can also modify the conductor that you have on the top here. And thankfully, it's very gracious and gives you a picture so it can show you some of the things that it's looking for. So the thickness of the copper, the width of the copper, the height of the substrate, the dielectric constant of the substrate, and things like that. Now, a lot of these are in micrometers for some reason, which I don't like, so I'm going to move them to millimeters. So if we move them to millimeters, we can see that on this left-hand side, we can tell it some of the things that we want. So if we want a 50 ohm transmission line, we want it to be 50 ohms at, let's say, 2.4 gigahertz again. Let's say we want the electrical length to be 90 degrees. If we click this right arrow here, then it will actually give us these two values that are underlined here, the physical length and the physical width. Now you'll notice that the height and the thickness aren't underlined, and that's because it's not solving for height and thickness, it's using those to solve. So let's say that we have a 1.65 millimeter substrate, something like that. So 1.65 millimeter substrate, the thickness of 35 micrometers, that's kind of fair. And let's try and run this one more time. We'll see that now the width has increased a little bit. So maybe the width can be 5.1 millimeters, and the length in this case can be 22.9. So let's make our width 5.1 millimeters, and the length 22.9. So now we're expecting this to be, we'll go ahead and connect this. We're expecting this to be, that's 100 minus J100 load. And then because of the way transmission lines act on the Smith chart, we're expecting that to be rotated around the center point by a certain amount, okay? So let's take a look at our results. So we'll go ahead and make a new graph here. Make a new graph, and we're going to be on the Smith chart for this one. I'll call it M line Smith for the transmit or the microstrip line Smith chart. Add our measurement. And what we'll do is we'll actually look at the S11 in this case. So the S11 for our microstrip match, because it's on the Smith chart, it's going to automatically move it. It accomplishes the same thing as the input impedance. So we're just going to take a look at our center frequency of 2.4 gigahertz. Take a look at 2.4 gigahertz, and we can add it here. So we're seeing I forgot something pretty major in this case. So right now we define the microstrip line that we have in our in our schematic. But our schematic only knows this microstrip line. It doesn't know the substrate that it's on, and the substrate can affect a lot of things whenever it's modeling. So we actually have to add a substrate model into our schematic here. Now, this is done very easily. We click on the Substrates tab. We don't have to click on this obsolete stuff. We can just click on Substrates. And we're going to go down to MSub, microstrip substrate definition. And we'll move this into our schematic. And you can move it anywhere. It's going to be defining it for the entire schematic. It doesn't have to be connected anywhere. Now, we do have to populate some of this information. So epsilon r is a pretty important one. So epsilon r, if we open up our TX line tool, we modeled it using 2.16. So we want to make sure this matches 2.16. Our height, I believe we said 1.65. So our height is 1.65, 35 micrometer thickness. And thankfully, a lot of these variables are the same as they are in the transmission line tool, so it makes copying it a little bit easier. our tan delta, 0.001. And then our epsilon r nominal, we're just going to make that the same thing. So you're typically going to keep that the same. Now, once we've added this the substrate definition, now it has enough information to actually plug it into the closed form solution for this microstrip line. So it should be able to solve it in this case. I'm going to close L network here. So it should be able to solve it in this case. And we can see that now our input impedance, or our input S11, is placed here on the Smith chart. Let's do a little bit of experimenting and see the effect of this length. The effect that this length has, excuse me, the effect that this length has on the S11 here on our result. So if we use the tune tool, I'll go back and make sure I talk about what I just did. So if we use the tune tool on our schematic, we can actually make this blue. So we can actually tune the length. You can tune the width too if you wanted to, but we're not going to. We can tune the length here, come over to our Smith chart, and we can actually use the tuner, and we can see that as we, as we drop this down to 0, so as the length is 0, we get right back to this original point, so where we're at that 100 minus J 100 impedance. And as we increase this length, we are actually going to be rotating pretty much around the circle here. And if I make this an absurd value, like 450 millimeters, you can see that it just continues rotating around that center point. Okay, so it's going to continue rotating around that center point there. Make this 45 millimeters here, and we'll make our step size 0.1. That 0.1 millimeters is a pretty good step size to take into account. Now, what we can see is that we need to think about this sort of as engineers. So we need to think about this as RF engineers, how we might match this load using only transmission lines. So we know that this transmission line section that we've added is going to rotate us around the center point of that Smith chart. Now, if we add a microstrip line in parallel, then we can add some reactance to it. So a microstrip line that's open on the end, that length is going to add some reactance to it. Okay, so it's going to act like either a capacitor or an inductor depending on the length of it. We can use that to our advantage. Now, I'm going to, one more time, go to Options, add the admittance grid, because that's usually pretty good for us, especially if we're adding something in parallel. If we go OK, now if I use this tuner, I can get to the point where I am pretty close to being exactly on this constant conductance circle here that's going to get us matched if we add something in parallel to it. So that's at 12.5 millimeters for me. I can unclick tune, so now that value is set in stone. And what I can do here is I can actually come back to our schematic, make sure that tool's closed, and I'm just going to copy and paste this one here. I'm going to add it to this point. So now we have our microstrip line from the load, and then we have another microstrip line in parallel, and it's open on the end. Let's go ahead and make, we'll keep the width the same. We'll make this length 0, because if it's open with the length of 0, it's like it's not even there. And now let's retry it. Well, before we retry it, let's go ahead and tune this length here so we can see the impact of it. So we're expecting it to be in pretty much the same spot, and our impedance is still pretty much in the same spot. Let's see if I can actually increase this marker size. So if I want to increase this marker size, I can right-click, click Options, go to Trace, and now what I'll do is I can click this first trace that I want, and I can change this size to, let's say, 10. I can press Apply, and now it's a little bit larger here, or let's see if I can make it, a little bit larger. If I change the weight, perhaps. Okay, maybe we're just out of luck. So I'll just make it a little bit larger and make it 10. Okay, so if we hit Apply, now we can see this marker here, although it's a little bit tougher to tell where the center is. That's okay. We can see that our marker is on this line, and it pretty much has had no effect, since that length is 0. But as we increase this length, what we'll see is that now we're moving along this constant admittance circle. We're adding some level of a complex admittance into the circuit. And if we get close enough, we can't make it a negative value, but if we wrap around this circle enough and we get to about, let's say, 31.1, I get a little bit closer to give myself a little bit more fine-tuning ability. 31, 31.1, 31.2. 31.1 looks like we got pretty stinking close to it. Now, this is kind of a good way of matching this transmission line, using realistic transmission lines. And we're hoping that if we add, let's say, another length of 50 ohm transmission line at the input, it's not going to matter because 50 ohms through a 50 ohm transmission line should still be 50 ohms. We can see that there's a little bit of rotation, a little bit of change, but it's still, for all intents and purposes, pretty stinking close to 50 ohms. Now, what we'll see is that, unfortunately, this isn't 100% accurate to the real case. So there's some things we can do to actually improve the simulation and make it a little bit better match for a realistic case, which is important because once you're fabricating things, you're spending real money, and that's going to be a pretty bad thing if you're spending money and it comes out not working. So there's always more things that we can do to make our simulation a little bit more accurate, and thankfully AWR has incorporated some of that into their standard libraries. So one of the things that we'll notice, you may have noticed this before, is that all of these three transmission lines are in purple. And because they're in purple, that actually means that they can be modeled in a real layout. So layouts are going to be pretty important later on because you're going to want to make sure that things are as pretty much perfect as can be. So if we take a look at the schematic, we can't really tell what it looks like physically yet. But if we come up here to the top, we can see that there's a button called View Layout. And that View Layout button is really, really handy because it allows us to actually see how this looks in real life. So let's click View Layout. And right now it doesn't look like we have much, but we can see that we actually have 3 links of transmission line. So we have 3 links of transmission line, and these little red areas show us how things need to be connected. So we can see that this one, we can see that this one needs to be connected by being rotated. And the way that we can rotate it is by selecting it, pressing Control R, and it's a little bit weird. So you have to grab it, hold, and then you have to manually rotate it around an axis like this. Okay, so I like to grab it, hold, and then extend and rotate it a little bit. Now we can rotate it by 90 degrees, move it right where it needs to be. And what we can see is that there's actually now a whole lot of overlap, right? So there's a whole lot of overlap in these. And the reason for that is because we haven't modeled it perfectly, right? So right now we're just looking at these lengths of transmission line. But in reality, you're going to have a junction separating these. And that junction is going to add some length that you maybe didn't account for, add some width, or maybe add some parasitics because of the sharp corners. So we can actually add that into our schematic, make it a little bit easier. Or make it a little, not easier, it's definitely not easier, but it's going to be a little bit more connected with reality. So let's delete these traces here. If we come back to our microstrip library, we can go to junctions. And what we're looking for is MT. We have microstrip T junction closed form. And if we use this version, it's actually going to ask us to manually define the widths of the T. And in this case, thankfully, the widths are all the same, so we can make it 5.1. Tab moves you to the next one, 5.1, 5.1. And now, if we take a look at our layout here, now we have this extra little element here that allows us to make these connections. And now things look a little bit more realistic, right? We don't have this crazy overlap and things like that that's not realistic in real life. So this looks a little bit more realistic. But we'll see that this maybe makes it a little bit harder for us to do our work because we have to manually enter all these widths. So if you have a well-defined schematic, and it does have to be well-defined, you can use this MT with the $sign. So that's an intelligent microstrip T. And what it does is it will actually look at the transmission lines connecting it, and it will say, I know that this one on my right is 5.1 millimeters. So I'm going to make the edge on this side 5.1 millimeters. Same thing on this other side. I'm going to make it 5.8 or something like that if it needs to be. So now we don't have to manually define it, but our schematic does have to be well-defined and well-constrained. If we look at our layout, we'll see that, oops, maybe we need to update it again. Let's see if we can see it in our layout. There we go. Okay, so now it's appearing in our layout. And it looks pretty much the exact same because those parameters are the exact same. Now, we're not quite done here yet. This has definitely gotten us closer to a step in the right direction, and we'll see that if we were to just simulate it right now, our match isn't nearly as good as we thought it was, right? So there's some things we still need to tweak. Now, one last thing I suggest you add here is if you're going to be using this open microstrip transmission line, that open is going to have some fringing fields that need to be modeled. And thankfully, AWR, again, has some models built in. If we go into Other, we can look for something called M-Open, and it's a microstrip open circuit with an end effect. And all we have to do is we have to add it to the end here. Tell it the width is 5.1. You could also use the M-Open that's intelligent, but I'm just going to use this regular one here. And in our layout, it does have this little blank thing that now has to be added, but we can either use this here and manually add it ourselves, or you can do what I like to do. You can just maybe go click home, see everything. You can highlight everything and press this button here, snap together, and it'll automatically snap everything together as best as it can. It won't do everything. It'll make some mistakes, but it'll get you pretty close for simple things like this. Now what we'll see is that after adding that open effect, it changed our it changed our match yet again. So hopefully this is going to get us a little bit closer. If you want it to be exact, you would want to use an EM simulation to actually maybe solve for full wave analysis in 3D space, but that's a lot more complex. If we use these closed form equations, then we can get a little bit closer without having to do too much more computation. So now, what we're going to want to be changing, we know that this ideally isn't going to have any impact here. This transmission line is 50 ohms, and we're expecting it to be 50 ohms regardless if we're matched to 50 ohms here. So let's go ahead and make this pretty long. Let's say 25. Now, what we can change, we know that we want these to stay at 50 ohms, so we don't want to change the width, but we can change the links. And we can change the links here. And this may not be the most exact solution that there is, but it does work to kind of get things going pretty well, pretty easily. So because we have this because we have this long strip of transmission line, we don't exactly see the input impedance here, which is tough. But like you said, having this junction here adds a little bit of extra transmission line anyway, which adds some delay. So let's go ahead and get rid of that long one. Maybe make it a little bit closer to reality. Uh-oh, variable not found. Oops. Okay, like you said, this one, even though it's intelligent, if it's not well defined, it's going to be a little bit tougher. So let's just make the length 0, act like it's not even there, but it still knows the width, and hopefully it'll work. Okay, great. So now we're working a little bit closer. Now we have these two parameters that we can tune here. If we have these two parameters we can tune, you can see that this first one that we're tuning follows a circle in this way. And what we can actually find is that, thankfully enough, if we get to this position here where we're at 10, maybe if we tweak this just a little bit more, touch more. Oh, we need a wider step in this case. Let's just make it 0 and 30. Oh, no, that's fine. If we just tweak these values slowly but surely, we can get to a point to where even without having to maybe do some manual analysis and some theoretical analysis, we can get really, really close to being matched almost exactly. And if I make this a little bit closer, maybe 10 and 11, get me a little bit more fine-tuning capability, 30 and 31, we'll see just how good of a match I can get. Let's see if I move it there. I move this one a little bit further up, move this one down. It's definitely not an exact science. Once you get down to it, there are definitely exact solutions. But whenever you're tuning and you have these junction effects and things like that, a lot of times just tuning and getting it as close as you can be your best friend, especially for a solution like this. So now we'll see that our real part is 0.994, pretty close. Our reactance is 0.006, again, pretty close to 0. And if we just want to verify this one last time, we can make a new graph. We can call it M line S11, make it rectangular, and we'll see just how good of a match we can get. So microstrip match, we're going to use, let's just check the magnitude of S11 in dB. So we run this, we can see that at this center frequency here of 2.4, we have minus 46 dB. So that's a pretty good input match here. Although as you get wider out, our minus 10 dB bandwidth is not nearly as wide as it was before, but that's going to be due a lot of part to that microstrip line and the impacts that it has there. We don't have as broad of a bandwidth, but we do have a really good match at that center frequency. And still with, let's see, we have about 128 on one side and then 200 and something on the other side. So still a pretty respectable bandwidth, but not as good as we could have gotten. So that's going to be one of the trade-offs of having transmission lines. So I think we've covered just about everything that I wanted to take a look at. If we take one last look at the layout view once we get done tuning these, then you can see that once we get our layout view up and running, I'm going to close this because it seems like not everything went over. Oh, let's make this 25 one last time and just verify our S11, make sure it's still good to go. Now if we take a look at our layout, what we'll see is that if we just hit Control A and snap together, thankfully it's simple enough to where it all does snap together. And if we had a load modeled here, we could actually see the load in this case, but in this case, it's good enough to see how we can use this realistic transmission line to model this load and how we can model this input match. So I think we covered just about everything that I wanted to get through, so I'm going to go ahead and leave it here because I know we already covered quite a bit of information. If you guys have any questions, please feel free to reach out to me either through email or in the comments on this video. I'm more than happy to answer anything because AWR, for all the power that it has, doesn't always have the best documentation for things. So if you're running into an error, odds are someone else has run into it before, and I can help you figure that error out and get you up and running again. If you guys enjoyed this, please feel free to give me a thumbs up. Anything like that helps keep me motivated and helps make me know I'm doing a good job and helps make me want to make more of these. Other than that, thank you guys for watching, and I hope I'll see you guys next time.